Hi, this is lecture 11, part 2, warehouse space and layout planning for IE 4355 facilities planning. As always, we start our lecture with the discussion of the course objectives and relating those with the material that is going to be covered in this session. So in this lecture, we are going to be addressing the first objective for this class, which is to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. So the agenda for this second part of the warehouse lecture is an introduction. We are going to talk about the warehouse layout model and storage systems. The objectives, learning objectives, is to learn warehouse operation improvement through the application of best practice procedures and available material handling systems for warehousing operations. So the introduction. There are different types of storage as we discussed in the previous video. First, randomized or floating storage. This is used when a product unit, SKU, or stock keeping unit can be stored in any available storage location. Number two is what we know as the dedicated storage, which is used when a unit of product or stock keeping unit is assigned to a specific storage location or set of locations. And the number three are variations of dedicated storage, storage according to part number sequence, and storage according to level of activity, storage and retrievals per unit time, and inventory level. So this is the third type that we are going to be discussing in this lecture. So for dedicated storage, we have the following. So if we look at this illustration, you'll see that the colors are grouped together. So for example, if you look at this green, you see that all the greens are together. This darker blue is also have all the items grouped together, the gray, the light gray, and so on. So for dedicated storage, each part or each SKU will have an assigned location, and it's going to be an assigned space in which you're going to put all the items for that product, and they're going to be located close to each other. For random storage, that's not the case. You see in this picture that there's a mix of colors happening. And you can see all the greens are not together. Actually, you see that in the greens case, there's less space assigned to it. There's some similarities in the way they're located when compared to this one, but you see that there's less integration in terms of the units being together. So the objectives of warehouse layout planning is space effectiveness, material handling efficiency, cost minimization, flexibility, and housekeeping. So in the next slide, or in the next few slides, we're going to discuss the quantitative warehouse layout planning model. So the warehouse layout model is an optimization model in which we have a dedicated storage, which is a set of storage locations assigned to a specific product. The decision variable of this model is xjk, and it's a binary variable that assumes values of 0 or 1s if product J is assigned to location K. if that product, let's say product 1 is assigned to location 15, if that's the case, then x115 is going to be equal to 1. If that's not the case, then that decision variable is going to be equal to 0. And the objective function, or the measure of effectiveness for this model, is to minimize the total expected distance traveled from the input and output doors to the location of these items. So what is the input data? We have Q, which is the number of storage locations. We have N, which is the number of products. We have M, which is the number of input-output points, or docks. These are the entry points and the exit points in the warehouse. Sj is the number of storage locations required by product J. Tj is the number of trips in or out of the storage for product J. Pi is the percentage of travel in or out of storage to from point I. So basically for product I, what is the percentage of travel happening into the warehouse, and what is the percentage of travel happening out of the warehouse, to go outside the warehouse. So if your product, I mean, if you expect in most cases, you expect that product, the same amount of product that goes in, the same amount of product that goes out. So that probability will be 50% for each product. DIK is equal to the distance or time required to travel from point I to point location to location K. And note that we will use rectilinear distances between storage centroids. So the mathematical model is here. As stated earlier, we have an objective function that is trying to minimize the total distance traveled. And the first constraint in that gray box is looking at assigning only one product to one location. And we need, in this constraint right here, the pink one, basically what this is saying is that we need to assign Sj locations to the summation. So the summation of the assignments has to be equal to the total assignments that we need for each product. And as I mentioned, the decision variables are binary. So if we look at the objective function, there's this term right here, which is the summation from I equal to 1 to M, which is the multiplication of the probability of traveling in and out, and the distances from the location of the door to the location of the item. So we can name that summation, this part of the equation, Fk. So that's what we are doing. This is going to be equal to Fk. And then this will become the following. So if you substitute this Fk into this equation, then what you end up having is this summation of Fk times xjk. So if you expand this part of the equation, then you'll get this in red. This is the expansion. So why are we doing this? So solving optimization problems, if you are familiar with operation research, if you have taken IE 3340, I guess you're an industrial engineer, you see that solving these problems are difficult when you have multiple decision variables. So you need algorithms to solve those. So the simplex algorithm is the one that is commonly used to solve linear programming problems. But in this case, this is not a linear programming model, because the type of decision variables that you have here are integers, binary integer variables. So this is a binary integer programming model, and those are very difficult to solve. So what we show in this slide is a method, a solution procedure that is an algorithm specifically for this model, that if you follow this algorithm, you can obtain the optimal solution without having to use any of the branch and bound algorithms for solving integer programming models. So this is what we call a heuristic or a solution procedure that is, it is good in the sense that can give you a good solution or maybe an optimal solution very quickly. So the idea of the solution procedure is the following. And again, this solution procedure applies to this problem that we are discussing in this lecture. It doesn't apply to every integer programming model. So we relabel the products 1 to up to n according to the non-increasing order of their TJ by SJ values. So we look at this ratio for each one of the products and we organize those in non-increasing order. Find the value of FK, which is the expected distance traveled between location K and the docks. And then part C is assign the locations to product according to their F values from lowest to highest. So let's look at one example. In this case, we have a warehouse dimensions of 40 feet by 40 feet, and we have storage locations that are of a size of 10 feet by 10 feet. We have one receiving dock at the northeast corner of the layout and one shipping dock at the midpoint of the west side. There are two products, A and B, and product A has 100 pallets a week. That's what we receive. And product B, we receive 80 pallets per week. Product A requires 10 storage bays, so SA equals 10, and product B requires 4 storage bays, which SB equals 4. So these are the warehouse dimensions again, and this is the storage locations. So they are 10 by 10. So what we have to do now is to compute this, compute the information we need to apply the algorithm. So we need the value of FK, which is gonna be equal to the summation of I equals 1 to M of PI DIK. So for that, we need some information about the probabilities, right? That PI. And what we are going to do is we are going to assume that everything that goes in goes out. So the probability of going from this door to the location of the item is going to be 50%. And the probability of going from the location of the item to the exit door is also 50%. And now we need to also compute the distances from the location of the entry door to the location of the item. So for instance, if I want to compute this for every location in the warehouse, so FKP1 times D1K plus P2 D2K. For this location here in the warehouse, I have to find the rectilinear distances. So we know these are 10 by 10. So if I go in this direction, this is going to be 5, then 15, then 25, then 35, and then 40 to get to this point. Okay, so for F1, for that first location, probability is 0.5, and the first distance is equal to 40. Now I have to compute the distance from going from that location to the exit door. So we have 5, 10, 15, and 20. So probability of exit is also 0.5 or 50%. And this times 20, this is going to be equal to 30. So we can compute this. I mean, we have to follow this process to compute the F value for each one of the locations. So I'm going to show you, let's say I do F15. So for F15, you will go from here. Let me change the color. This is gonna be 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So this is gonna be 0.5 times 50 plus 0.5. And now I have to compute from this centroid to the exit. So 5, 10, 15, 20, 25, 30, 35, 40. So this is times 40. This is gonna be equal to 45. And for F16, this is gonna be 0.5 times 40 times plus 0.5 times 50, and it's also equal to 45. So using this information, I can fill out the values for each one of the cells. And that's what I'm going to do here. So this is going to be, as we saw here, F1 is going to be 30. F15 is going to be 45. And this is also 45. The rest of the numbers, I'm just going to fill them up, but you know how to compute those now by following this process. So for 2, this is going to be 30. For 3, this is also 30. For 4, this is also 30. Actually, for this and this and this and this, we have 30. We have 35 here, 35, 35, 35, and 45, and 45. So those are the values for the F value for each one of the cells. So now the question, now that we have that information and following this algorithm, we just completed part B, find the values of FK for all the locations. And now we are going to assign the locations to product according to their F values from the lowest to the highest. The lowest to the highest, meaning that part A, that we are ordering the products based on this non-increasing order of the ratios for TJ, SJ. So what I'm going to do is I'm going to compute the ratios for both products. So we have the ratio for A and we have the ratio for B. And we are going to assign first the locations for B because they have a higher ratio. And then after assigning the locations for B, I'm going to assign the locations for A. Okay, so what we have is the following. I want to assign B to those cells that have the lowest FK value. So I'm going to use another color. So I have 4 cells, right? For B, I need to accommodate 4 cells. And I'm going to look at the lowest values, which is 30. So I can put B here, B here, B here, and B here. And now I can use the rest of the cells for A. And remember, we assigned first B because the ratio TB, the ratio T by S is greater than the ratio for the ratio of B. The ratio TB SB for product B is higher than the ratio for TA SA. So I have the 4 cells, and then I can assign the 10 cells needed for A as follows. So A will be here, 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 here. And I'm going to occupy those that have low values first. So I have 8 until this point, so I will need 2 extra cells to complete the cells required by A. So I did A by looking at the lowest values, and then I assigned those 10, making sure that it shows the lowest values possible. And I completed the assignment, and we still have 2 extra cells that can be used for other products. If you want to look into the textbook, there's another example. You can verify the calculations shown in figure 10.29b and verify the solution shown in figure 10.29c. Now, the last part of this lecture is on storage systems. So I'm just going to go through some of the technology available in terms of arranging items in a warehouse. So some of them include the rack storage, the carousels, and the ASRS, or automatic storage retrieval systems. So rack storage systems, one of the primary methods of material storage, utilizes the vertical space in the warehouse and is highly cost effective, highly cost efficient. There are multiple rack types. So they are listed here: walk-through racks, pushback racks, very narrow aisle racks, driven-in racks, and gravity flow racks. Mobile, double deep racks, roll-out shelf racks, rail racks, and cantilever racks. So this is an example of walk-through racks. These provide easy accessibility to the adjacent aisles. Picking time is greatly reduced and allows more likely into the aisles. Higher utilization. It also provides higher utilization of the vertical space of the warehouse. The pushback racks, these are the ones in which you have some type of level that allows you to pick up in some cases, or you are able to pick up the first item first and then push and move forward the rest of the items. Pallet loads are literally pushed back into the rack. When pallet is retrieved, the deeper pallet load automatically advances to the aisle. High density and high accessibility. It is used to store large number of pallets for a long time and then remove and ship them as seasonal product. This is used mostly in combination with driving racks. The very narrow aisle racks. These permit aisles with less than 5 feet, provide significant floor space reduction, use it at heights of 40 feet to 50 feet. Pallets are accessed with turret or side loader lift trucks. Sometimes racks are designed with top and bottom monorails, so you can move them around. The driving racks used for bulky and lightweight parts. Parts are mainly in cartons. Forklift is the material handling device used, and parts are typically stacked one over the other in large numbers. The gravity flow racks, these ones are used for parts in cartons. Parts are supported on rollers in the rack system. Material transfer is done with ease. Easy to move parts along the same row, as less effort is required due to the presence of rollers. The mobile racks, as you can see in this picture, you have some of those racks that can be moved as needed, so you can access the items. These provide high density storage systems, 100% utilization of pallet positions. Storage carriers are driven by electric motors. This is used mainly in cold or ultra cold warehouses where aisle space is at a premium. Used when speed or product movement is not a major concern. So why is this that the 4 item is very important? Because for you to maintain very cold temperatures or ultra cold warehouses, that has a big cost. So you want to make sure that every inch of that space is well utilized. Double deep racks, those are shown here. It's like placing 2 rows of racks together. Uses a deep reach lift truck for storage and retrieval. Increases floor space usage to about 60% to 65%. This is used for high throughput operations, has a low initial cost, provide high productivity and less equipment damage. The rollout shelf racks, these are specialized storage, mainly for delicate and costly parts. Use it for dies, measurement tools. The real racks, these are special type of storage, and it's mainly for cables and wires. The cantilever racks, these are used to storage long pipes and wood. Parts are stored using the forklift. It is highly economical and can be used till heights of 22 feet. Advantages of carousel storage. These are for high peak rates, motorized computer control and independent rotating aisles of shelving. Parts are carried to the picker rather than the picker going to the parts, like in the case of racks. Mostly set up in pots of 2 or 3, and pick rates vary from 80 to 100 picks per person an hour. These advantages, adding more people cannot significantly increase pick rate. Only 1 picker can operate at a given time, thus reduces the ability of the warehouse to respond to surges in demand. So this is an example of a horizontal carousel. Features, it is a series of rotating beams of adjustable shelves driven on top or bottom by a motor. Rotating takes place on an axis perpendicular to the floor at about 80 feet a minute. Horizontal lengths vary from 15 feet to 100 feet. Height varies from 6 feet to 25 feet. And prices start from $5,000 and increases with the number of beams and weight capacity. Automated storage and retrieval systems improve space utilization. 50% of rack space can be recovered. High saving in picker time. Allows quick access to goods via a system of shelves operating on shuttle mechanism. It brings the exact pick store location to the operator. It increases retrieval productivity by more than 2.5 times. Access area of the system is ergonomically designed to present stored items at an ideal height for picking, and it provides a high employee safety and improved throughput. So these are an example of the retrieval systems. So that's the last item for this lecture. And that's the conclusion. So in this lecture, we cover the warehouse layout model and also discuss some storage systems.